So finally, I have a system, single degree of freedom down system. This kx equals 0. I can write this system by dividing by m as x double dot plus 2 zeta omega n x dot plus omega n squared x equals 0. And the roots of this system, S1, 2 are negative zeta omega n plus minus I omega n square root of 1 minus zeta squared. That's for the underdamped system, the case we are interested in, or negative zeta omega n plus minus I, and we call this omega d. So graphically, I can represent the roots as, of course, in the complex plane, real, imaginary. If I have a root, then the real part of the roots will be zeta omega n. The imaginary part is omega d. And if I find distance r here by squaring and adding omega d squared plus zeta omega n squared, you will find that this will be omega n. And for angle alpha, if I take the cosine of alpha equals zeta omega n divided by omega n, which is zeta. So I can determine also the parameters of the system, frequency, the natural frequency, damping ratio, all by inspecting the location of the root of the characteristic equation. So let's consider an example, a system represented as 2x double dot plus 12x dot plus 50. X equals 0. First, I will normalize respect to x double dot. So divide by 2 x double dot plus 6x dot plus 25 x equals 0. Now, comparing this to the general form, I can determine that omega n squared is 25, which means that omega n is 5. 2 zeta omega n is 6, and omega n is already 5, so solving for zeta, zeta will be 0.6, and omega d is omega n square root of 1 minus zeta squared, which leads to, we have omega n 5, zeta 0.6, omega d equals 4. The other way of going around this is finding the roots of the characteristic equation. So this is option 2. The characteristic equation is s squared plus 6s plus 25 equals 0. And solve for s12, you will get negative 3 plus minus I 4. So we have a root at -3 and 4. So that means this will be 5. So reading the points here at the real imaginary plane, I can see that omega d is 4, omega n is 5, and zeta is the cosine of the angle alpha, which is 3 divided by 5, which is 0.6. So I can use either way to determine the parameters of the system. And knowing these parameters, I can write the response x of t as some amplitude x e to the power negative zeta omega n t. Negative zeta omega n t is negative 3t sine omega d is 4, so 4t plus some phase angle phi, and the magnitude of the response x and the phase angle phi can be determined for the given initial conditions of the problem. As we mentioned before, A was the initial position, B was zeta omega n x 0 plus v0 initial velocity divided by omega d, and x is the square root of a squared plus b squared, and v is the inverse tangent of a divided by b.